Alright, hello everyone. So in this video we go over a new section on infinite sequences and series, so particularly infinite sequences. About half of this section will be a basic review of what we learned back in an intermediate algebra course in which we went over a brief introduction into sequences. However, back then in an intermediate algebra course, we just covered how sequences behave, and we went over also more like finite sequence. Here we are going to look at sequences in a slightly different way. Of course, what we learned before is going to be useful, and what we learned this time is different notation, and we are going to determine whether a given sequence converges or diverges, something we didn't learn back in our intermediate algebra course. Okay, let's define what a sequence is. Okay, so a sequence is a function whose domain is the set of positive integers, right? Like any other function, you can plug in any number, of course, as long as it's in the domain, right? However, for sequences, the domain is only positive integers. Okay, so we have functional values that we denote as a sub 1, a sub 2, a sub 3, etc. That is the number of the element, or rather the term that belong to the sequence, like the first term, the second term, the third term, the fourth term, etc. So that's why the domain is only positive integers, because there's no such thing as the halved term or the 1.5th term. No, it's only the first, the second, the third, just integers. Okay, and in this class now we are going to change this notation and denote it at this subscript n equals 1 or n equals 0, depending on the value in which the sequence begins, and going to infinity. Okay, so let's develop a few of the sequences that we have here. Let's just let's expand a few terms, and all we do is simply, so let's show about 4 terms of the sequence. All we do is plug in the first value of n that we have, in this case n equals 1. So this will be 1 divided by 1 plus 1, comma 2 divided by 2 plus 1, comma 3 divided by 3 plus 1, and 4 divided by 4 plus 1. And all we do is just simplify the numbers. So in this case, I'm going to say comma dot dot dot, because this sequence goes on forever. Okay, so let's just simplify 1/2, comma 2/3, comma 3/4, and 4/5, comma, this just goes on forever. Let's look at another example. So again, the first term we plug in is n equals 1. So this will be the square root of 1 divided by 2 to the 1 minus 1, the square root of 2 divided by 2 to the 2 minus 1, the square root of 3 divided by 2 to the 3 minus 1, and the square root of 4 divided by 2 to the 4 minus 1, comma dot dot dot, right? We don't have to expand infinitely many terms, of course, right? That's not the purpose, just to get familiar with how this works. So this is 1 divided by 2 to the 1 minus 1, which is 2 to the 0, square root of 2, we can just leave it as square root of 2, to the 2 minus 1, which is 1, comma, square root of 3 divided by 2 to the 3 minus 1, which is 2, comma, square root of 4, which in this case is 2, we can simplify this one, and divided by 2 to the 4 minus 1, which is 3, comma, dot dot dot. This goes on forever. And let's just simplify. 2 to the 0 is 1. 1 divided by 1 is simply 1. Square root of 2 over 2 is just itself, and then square root of 3 divided by 2 squared, which is 4, and then 2 divided by 3 by 2 to the 3rd power, which is 2/8. And you might want to divide this to simplify this to 1/4 if you will. Why not? It changes to 1/4. It's all right. Okay, and dot dot dot, because this in this case goes on forever. So what did we do essentially? Okay, let me recap. So here we plug in n equals 1, here we plug in n equals 2, here we plug in n equals 3, here we plug in n equals 4, and so on and so forth. Likewise, here we started plugging in n equals 1, n equals 2, n equals to 3, n equals to 4, and so on if we were to plug in even more values, which just keep it like this, okay? So let's see, what about the next example, letter C. So notice in this case, unlike the previous examples, the sequence doesn't start at 0 or 1, it starts at 2. So this is what we're going to do. And also be careful with this factor right here, this negative 1 to the nth power. This is what we call typically alternating factor. This is an alternating factor. This is what's going to make a sequence positive or negative, right? If we raise negative 1 to an odd power, we get negative. If we raise negative 1 to an even power, we get positive. So we start with n equals 2. So we expand this to negative 1 to the second power times the square root of 2 minus 2, comma, negative 1 to the third power times the square root of 3 minus 2, comma, negative 1 to the fourth power, square root of 4 minus 2, and negative 1 to the fifth power, and 5 minus 2. So just 4 terms, comma, dot, dot, dot. This goes on forever. So in this case, what do we have? We have negative 1 to the second power, which is going to turn this into a positive, and then 2 minus 2, that's going to be the square root of 0, comma, negative 1 to an odd power is going to be a negative 1 that multiplies the square root of 3 minus 2, which is 1, comma, negative raised to an even power, that's a positive, and that's going to be the square root of 4 minus 2, comma, and then an odd, and that's going to be negative, and then 5 minus 2, that's 3. So let's see, oh, wait a minute, I think I could have simplified this right away. Why not? So let's see. So the square root of 0 is 0, square root of 1 is 1, the square root of 2 is simply 2, the square root of negative 3, the negative square root of 3 is negative square root of 3 simply, right? And this goes on forever. So again, what did we do? We plug in n equals 2. In this case, we started at 2, right? And then n equals 3, n equals 4, n equals 5. All right, so now we're going to do the reverse. So we are going to be given a sequence. They are asking us to find out the expression that gives out these terms when this sequence of terms when we expand the sequence. Okay, so here is where we will need our pattern recognition skills. Okay, so let's see. Number one, it would be a good idea to divide this by 1, right? Which is the same as the square root of 1. I'm going to put the square root of 1. This way you can see a very interesting pattern, that is the square root of 1, the square root of 2, the square root of 3, and then the square root of 4. So looks like the general rule here. So by the way we use curly braces, the denominator will have a square root of n. Okay, but notice something interesting in the pattern. So for the first term, we have the square root of 1 in the denominator, and the quantity in the numerator is 1 more, which is 2. It is the same for the second term. We have a 2 inside of the radical, and then the number in the numerator is one integer more. And same for the third term, and so on. So in this case, I would say n plus 1 will be the rule. And in this case, we're starting our sequence at n equals 1 and finishing the sequence all the way to infinity. Okay. Now for the next example, there is a typo here. These were supposed to be all ones. So please correct that on your paper if you printed it out. So, all right, I'm gonna do the same as I did in the previous example. I'm gonna add this 1. Okay, and you might recognize this sequence of numbers, right? 1, 8, 27, and 64. What are they? I think this is 1 cubed, this is 2 cubed, this is 3 cubed, and 4 cubed. So in the numerator, we will always have a 1 that never changes. The denominator is just n cubed. Starts at n equals 1, goes all the way to infinity. All right. Now, what do we have for the third example? So divide this by 1, right? So you can see a pattern. We have 1, 2, 3, 4. That's nothing other than n in the denominator. Notice the space I left here, I left it for a reason, and there's a 1 in the numerator because notice in the numerator of each term we have 1, 1, 1, 1, always 1. However, if you look at each term of the sequence, it's an alternating sequence. We have a positive, then a negative, and then a positive, and then a negative. So we are going to use one of those alternating factors like the one we have here, right? Like this negative 1 to the n power. Now, let's determine whether this would work. So negative 1 to the n power. Started at n equals 1 and going all the way to infinity. The thing is, if I plug in the first number, n equals 1, right? What am I going to have? Negative 1 to the first power, that's an odd power, I will get a negative. But the thing is, I have a positive term in the very front, right? Not a negative. So we need to fix this. So there's something we could do in order to fix this. The only thing we can do is add 1 to the exponent. Because if you add 1, that is 1 plus 1 equals 2. That's an even power. And negative 1 to an even power, it's the positive term that we have here at the beginning as the first term, right? So that's how we fix that. All right, so this is it pretty much about sequences, right? And how do we work? It's just listing the terms. Typically we list between 4 and no more than 6. So that's enough just to see the pattern, just to see how the numbers either get big or get small, right? And that's pretty much the next point, whether they get big or whether they get somewhere, right? That is converges or diverges. By the way, there's a little typo right here. It shouldn't say Taylor polynomial. This is, well, the limit of a sequence, right? Just be sure to change that. Okay, and so we're going to have a sequence given by the rule a sub n. Okay, whatever sequence we have. So the sequence converges if the limit that we have here, the limit to infinity, exists. Otherwise, if the limit doesn't exist, that is, we get an infinity or something, then the sequence diverges. Okay, let's look at a few examples. So we are given a sequence. Let's write it in limit form. So limit of 1 over n as n approaches infinity. If we plug in the number, plug in infinity, 1 over infinity, what do we get? This is equal to 0. And in this case, 0 is a number, so the sequence converges. Okay, the sequence converges. All right. What about the next one? Okay, so let's write this as a limit square root of n as n approaches infinity. Okay, so if we plug in square root of infinity, what do we get? Infinity. So in other words, the limit does not exist. So in this case, the sequence diverges. What about the next one? Letter C will be a tricky one. Let's see how this works. We only have the sequence -1 to the n power. So we have limit -1 to the n power n approaches infinity. So this is going to be a little bit weird. -1 to the infinity. What is this? Okay, so let's see what's going to happen. If I plug in 1, I'm going to get -1. If I plug in 2, I get +1, and then -1, and then +1, and then -1, +1, -1, and so on and so forth. Do you see what this sequence doing? It's simply bouncing back and forth between +1 and -1. I'm going to illustrate this with another example as soon as we're done with it. Well, let me actually do it. Okay, let's look the first example, 1 over n. So let's relate this to the corresponding function f of x equals 1 over x, right? Whose graph looks like this. But in this case, we are going to refer to the sequence, not really the function f of x, because for the function f of x, the domain of it will be no other than any number in the domain that we can plug in except 0. However, for the sequence, okay, let me call this 1, 2, 3, 4, 5, and 6. 1, 2, 3, and 4. Okay, so what is going to happen here if I plug in n equals 1? So I'm going to have 1 over 1, which is 1. So 1 comma 1. Okay, and then n equals 2. I'm going to have 1 over 2, which is 1/2, right? That is going to be somewhere here. And then n equals 3. This will be 1/3. So 1/3 will be exactly here. And then n equals 4. That is 1/4. So that should be somewhere, maybe, I don't know, here. And then n equals 5. We are going to have 1/5. See how this sequence is approaching 0 as we got it here on the limit. So here, this sequence converges to 0 as we approach infinity, as we add infinitely many terms. What about this sequence now? -1 to the n. Okay, so let me do 1, 2, 3, 4, 5, 6, 7. That's enough. Okay, so -1 to the first power is going to give us -1. Okay, let me label this as -1 and 1. So in this case, we get -1, and then -1 to the second power is going to give us a positive number, and then a negative number, and then a positive number, and then a negative number, and then a positive number, negative number, and so on and so forth. This is what the sequence is going to do for the rest of the number lines forever as we approach infinity. So as opposed to the previous example, right, as opposed to this case, here this sequence seems to approach 0. Visually seems, however, analytically, by finding the limit, we found out that the sequence converges to 0. Here, this is just bouncing back and forth between -1 and 1, so it's not getting anywhere. It's diverging. So that's why the sequence diverges. Okay. Let's look at letter D. Letter D, limit of 4 minus 1 over 5 to the n as n approaches infinity. And what is going to happen here? So 4 minus 1 over 5 to the infinity, as we did earlier in the semester when we reviewed limits to infinity. So -1 to the 5 divided 5 to the infinity, it's simply infinity, which goes to 0. So the final answer is 4. Okay. Let's look one with a polynomial. Limit 3n squared times 3n squared plus n minus 1 divided by 6n squared plus n plus 1 divided by, as n approaches infinity. Okay, how do we evaluate limits that contain polynomials? So there's many different approaches. One of them is to basically neglect these terms and observe the exponents, focus only on the leading terms. That is 3n squared divided by 6n squared, cancel the n squares, we get 3 over 6, which reduces to 1/2. However, we need to show this work in a more formal way. How do we do that? Well, factor the highest power of the variable in both the numerator and denominator, that is n squared. We get 3 plus n 1 over n and minus 1 over n squared. Okay, so if we distribute this back, we get n times 1 over n, cancel one of the powers, we get n. And then n squared times 1 over n squared, basically the n squares cancel and we get simply -1. If we think about this in a backwards way. And likewise for the denominator, factor out n squared, 6 plus 1 over n, plus 1 over n squared, as n approaches infinity. Alright, in this case, I'm not going to substitute the number infinity. I'm just going to see what is going to happen. Number 1, let's divide out these n squares. So we're going to have limit 3 plus 1 over n minus 1 over n squared divided by 6 plus 1 over n plus 1 over n squared. As n approaches infinity, so this term goes to 0, this term goes to 0, that term goes to 0, that term goes to 0, because 1 over infinity, 1 over big, we get nothing. And all we remain with is 3 divided by 6, which is 1/2, as we got earlier by neglecting the other terms but the leading ones. Okay, however, this is how we show the work. Alright, so let's look at letter F. Letter F and G, if you look at them, if you observe them, they look very, very similar. How do they differ? Okay, let's have a look. Alright, let's write it down in terms of limits. So 2 to the n divided by 5 to the n as n approaches infinity. And limit of 7 to the n divided by 3 to the n as n approaches infinity. Okay, we need to have a very good understanding of these two to see the differences between these two, because in the next section we are going to use this when defining and describing a geometric series and determine whether they converge and diverge. So what is going to happen in this case? Well, I'm going to plug in the infinities here. So 2 to the infinity, 5 to the infinity. and 7 to the infinity divided by 3 to the infinity. Okay. Of course, if we evaluate these quantities, we're going to get infinity over infinity, and that is going to be one of the indeterminate forms. However, in this case, we can tell which one diverges and which one converges. Okay, and how can we tell that? Because in this case, notice this is bigger, right? This is larger. This is smaller. How do we know? Well, look at the base. 2 is smaller than 5. So in this case, this will converge. Because we would be dividing by a larger quantity, by a huge quantity, and if we divide by a huge quantity, the quantity gets smaller. What about this in the next example? In this case, this is larger. In this case, this is smaller. What is going to happen here? So notice how, again, this is a larger and this is a smaller. So in this case, we have a huge number being divided by a smaller number. So the numerator wins in this case. So this is going to get bigger and bigger every time. So this will otherwise diverge. So we will apply this in more detail when we cover geometric series in the next section. So this is the end of this section. Just a brief review of sequences, and extend the concept to give that infinity character to these sequences. I'll see you on the next video. Bye.